Hi, AP Stat students. Welcome to What is the Question Asking Part 3. This is going to be the final one for the year 2020. It's probably going to be a little longer. I have a lot of questions on here, but it's pretty close to being cumulative. I don't spend as long on the inference because I've done a lot of inference in the other ones, but trying to just not reteach anything here, but saying, hey, here's what the question's asking, here's what they're looking for. At this point, your test is only a couple days away. You're not necessarily going to learn new things, but there are some things on here that are relatively easy that can just refresh your memory. And for the year 2020, which is great, is you have an open notes test. So you can write some things down and really make sure that you're organized in your thoughts. Okay, so let's begin. This one here is, it's a number one question. Typically on an EP test, there's 6 questions, right? And the first question is really about exploring relationships. I'm not going to read through the question. I'm just going to say, hey, here they give you 2 box plots, right? And part A says, write a few sentences to compare the distributions. I've said it before. I'll say it again. When they say compare and you have distributions here, you have 2 box plots. You want to use socks, S, O, C, and S. You want to talk about the spread, or I'm sorry, the shape. It's late at night. Okay. The shape. This one's skewed which way? Left, right? And the other one is more symmetric. Okay. So again, you would need to talk about this in context. The 1 cup is skewed left. The 3/4 of the cup is more symmetric. There are no outliers in either of the distribution. The center for the 1 cup, that median right there, that's what you're going to use because they give you the box plot. The median is greater than the median for the 3/4 cup. Notice I use the word greater when we compare. Okay. The IQR, the spread now for the 1 cup is greater than the spread for the 3/4 cup. Addressing SOCS, you're not using bullet points. You're talking about it in context with comparison words. Okay. Next, again, I'm not going to read through. I'm just going to highlight some important things about what the question is asking. They multiply one of the distributions, the 3/4 cup, by 4/3. Okay. It's important to note. B, what new information about the sugar content do the box plots provide? Okay, so if you look up here and you look at the 3/4 cup, what has happened? Okay, the median has increased as well as that spread has increased. What should we learn from that? When you are doing a transformation on any data, right? Okay, so you're taking that data and you're either multiplying or adding. Multiplying changes the center and the spread. Okay, adding only changes the center. It does not change that spread. So you would just talk about how both have increased compared to what was before. Part C, how would you expect the mean amounts of sugar per cup to compare for the different recommended serving sizes? Okay, based on these box plots right here. This is getting at, do you understand when something is skewed versus symmetric and how do the mean and the median compare? Okay, so if I look here, the medians are very close, right, to each other. Very, very close, just a little bit apart. But the difference is the 1 cup is skewed left. Okay, so what happens then? The mean chases the tail. Okay, so the mean is going to be less than the median. Now, I don't know that it's right there, but I do know that it's going to be less than. And now the 3/4 cup is symmetric. And what do we know about symmetric distributions? The mean and the median are approximately equal. So what can we say? The mean of the 1 cup is going to be less than the mean of the 3/4 cup. Explain why? Well, because the 1 cup is skewed left, which means the mean will be less than the median of the 1 cup, whereas the 3/4 cup is symmetric and the mean and the median will be approximately equal. All right, let's keep cruising. There's a lot to go through. I'm talking slow. I just want you to really think about it. I want you to be relaxed. I don't want you to be stressed. The test is going to be tomorrow for a lot of you watching this, okay? And I just want you to think, hey, what do I know? Like this stuff you guys know, this stuff you can process. You don't have to be too overwhelmed by that, okay? You can refresh your memory on that. Okay, let's move on here. This is another exploring data one. Describe a procedure that uses summary statistics to determine whether there are outliers. This one's just asking you, do you know the outlier rules? The lower fence and the upper fence, right? The lower fence, you take your quartile 1 minus 1.5 times the IQR. What is the IQR? Quartile 3 minus quartile 1. The upper fence, you take quartile 3 plus 1.5 times the IQR. If you have any outlier, any data, right, that is less than, oops, I should use a pen. Come on, computer. There we go. If we have any data that's less than the lower fence, that's an outlier. If we have any data that's greater than the upper fence, that's an outlier. Are there outliers in the data? Justify. You would just look at the data, you look at the minimum and the maximum, compare them to the lower fence and say yes or no, okay? Now, part C, I really want to talk about this for a couple seconds here. The news media reported that in a particular year, there were only 10 inches of rainfall. Use the information provided to comment on the report stated. Only 10 inches of rainfall. But what do you notice about the quartile 1? 9.680. That means 25% of the observations, the rainfall days, were at 9.680 or less than that, okay? That's a pretty high p-value, right? That's a pretty high probability, okay? So to say only 10 inches only makes it seem like it's unreasonable, okay, or not probable. It is probable that that could happen based off of quartile 1. So what is the question asking here? You have quartiles, you know their percentiles. Quartile 1 is 25%, median is 25 or 50%. Quartile 3, is 75%. Okay, let's move on. That was a quick one. Let's move on to talking about the normal distribution, okay? So this is talking about trains, they're carrying ore. One thing when you're reading a problem and you notice, okay, that it says normally distributed, you can pretty much count on, oh, my computer again, sorry. You can pretty much count on you are going to need to do a z-score and go to your table. Now, I think Jan's taught you guys how to use the normal CDF in your calculator. At this point, I'm not going to teach you that. Like your test is tomorrow, okay? So you do what you're comfortable with. I started off using the tables for the z-score chart, that was just a personal preference for me, okay? And they give us the mean, right? And they give us the standard deviation. And it's talking about what is the probability that the weight of the ore will be 70.7 tons or more. You're going to find a z-score. You're going to show your work. You're going to identify that you have a mean here, because here's the catch, you guys. Here's the catch. Sometimes the rubrics say identify what the mean and the standard deviation are before you go through the z-score for that normal distribution. And sometimes that's not in the rubric. So what I would just say is hey, I know that the mean is 70 and the standard deviation is 0.9. And then I'm going to go, to be honest, I would just draw that picture, okay? I'm going to find that z-score, okay, based off my observation zoms minus my mean divided by my standard deviation. I'm going to go to the table, and because it is, I think it says greater than, yeah, it's a greater than, okay, right? You go to that table, you find the p-value, and you need to do 1 minus that because why? It's a greater than problem, okay? Now, here, this question, I'm going to read through. It's using part A, and it's saying, would that fact make you suspect that the loading mechanism is overfilling? This is getting at that whole idea of a low probability. For example, if it's less than 5%, like with our p-values and our alpha, a low probability is unlikely to happen, okay? Is unlikely to happen. So talking about this question in terms of how big is the probability of part A, okay? If the probability is large, it's a likely event. If the probability is small, it's an unlikely event. Okay. Now, part C, you'll notice it's very similar, But the difference here is it talks about 10 cars instead of just one. So what do I need to do? Well, based off the central limit theorem, 10 cars is really not a big enough sample size, but it states that the problem is normally distributed. So it's okay to proceed with this question here. Okay. And so I'm going to go through and I would just do the same process I have here, but the catch is, this is slow, I'm sorry. Okay. The catch is when you do your z-score, right, you're going to take, where is it, 70.7 minus 70 divided by your standard deviation, but then because of that sample size, you have to divide it by the square root of 10. And again, the same answer, justifying your answer there, okay? All right, are we ready to move on? Good. Okay, let's get to some linear regression. All right, so they give us a line right here. And I don't think they're going to have you do this on the test this year, but it says draw a least squares regression line. So I did my best based off the computer because it's hard to do with my handy mouse here, okay? So I drew about half the dots above, half the dots below. And then part B, it's starting to talk about a residual, okay? And it gives us, I put it in purple, that plot there, 67, 61. It says circle the point, so I should have circled it, okay? That represents, and then draw a segment on the scatter plot that corresponds to the residual. A residual, what is a residual, okay? A residual is equal to your observed y, so y, minus your predicted y hat. So my observed y right here is at 71. How do I know that? Because that's what they told me right there. My predicted y is what the least squares regression line gives me right there. Now, two trains of thought here, or two trains of thought, excuse me. They actually give you your least squares regression line here, so you can actually figure out what this actually should be, what this plot should be. Because really, this is not like a technical line. I did my best to draw it, and part of me hates this question because I even remember doing this in class. If you would draw it, the y-intercept should be at 35.1. Okay, so, it's just, in my opinion, it's hard to draw. So I personally would do to find the actual residual to make it appropriate. I know that the observation is 84. So what am I going to do? I'm going to plug 84 into X here, and I'm going to find the actual predicted, because then it's more mathematically correct, okay? So I find my actual predicted after I plug 84 into X, and I chug that out, right? Plug and chug, okay? And then I'm going to take my observed 71 minus whatever came out to give the actual residual. Oh, dear. You guys, we're okay. I circled what was going on from 84 and 71 from part C when it's actually 67, 61. Forgive me. So I'm not going to plug 84 in there because that's from part C. Let's learn a lesson here. I'm not going to stop and edit this out. Let's learn a lesson. When we're on the test, make sure you're reading the right question, okay? Let's review. Let's rewind. I don't want anyone to panic because I made a small mistake here. I didn't teach you anything wrong. I just took the wrong numbers, okay? Again, we know this is the residual right here. We have an observed value. This point right here is a predicted value based off the line for the X value of not 84, but of 67, okay? We know the observed is 61. We need to find the predicted by taking 67 and plugging it in for X and figuring out what you get and putting it right here. And then you do 61 minus your predicted there. Now, if they'd ask you to interpret the residual, you would just say something to the extent of something how it over-predicted or under-predicted what happened when X was equal to 67. So in this case, okay, we're going to have a negative residual because this Y value is smaller than my predicted Y value. When we have a negative residual, our line then over predicts what should have happened. Okay, sorry about that, you guys. Part C. Suppose the point 8471 is added to the data set. So I did that right here in green, okay? Now my line is not the most perfect line. I'm not gonna lie about that. Um, if I'd redraw it by looking, because I did this quick because I'm just looking at what the question's asking. Okay. This is just really getting at knowing, is something an influential point? Okay. Does it have leverage? So on and so forth. So slope and correlation, they are affected by extreme observation. So for example, let's just say I put a point down here. If this was a point, that's going to bring my slope down, right? It's going to take that slope and it's going to bring it down, okay? What does that mean? The slope is going to increase. The y-intercepts, the slope is going to decrease, right? It's not going to be as steep. The y-intercept is going to increase. And the correlation is going to get bigger. Why? Because correlation is talking about basically the spread in between all those points. The tighter the points are together, the stronger the relationship is. Now all of a sudden I had another point there. Now the points are not as far together, or not as close together. Okay, so just knowing that, writing that down, reach out, because I made a little mistake on this one. Not huge. I didn't teach it wrong. I just used the wrong date at one point. I hope it didn't mess you up too much. Deep breath, relax. We are all good. And let's move to the next question. Okay. Here's another one about least squares regression line. Again, I'm not going to read through it. I just want to make sure that, again, that you understand how to read the Minitab output in case you see that on the test. This constant, this will always be your y-intercept, okay? Here, right here, this is going to be your slope, okay? And they actually gave you that least squares regression line up here, which is really nice, okay? Now, the first question saying, is the linear model appropriate? Whenever the question is asking about the linear model, okay, the linear model is talking about, if it's appropriate, that is, the residual plot. And what you want is you don't want to see any distinct pattern. Now, this is not a perfect pattern, but I do not see a distinct U. And the College Board is not going to mess with you, you guys. You're either going to see a distinct like U or fan, okay? So you have a lot of dots together and then it fans out. This one, I would say the linear model is pretty appropriate because there's no distinct pattern in the residual plot. So we talk about a shape of that U or that upside down U as being as a pattern, or that fan, that's a pattern, okay? So there's no distinct U, okay, or fan, which is say there's no distinct pattern. Therefore, the linear model is appropriate for prediction, okay? All right, I do want to quickly just talk about this R squared right there. Sometimes there are questions on the test where they might say to you, what is the correlation coefficient? So a couple of things. R squared can also be called the coefficient of determination. The correlation coefficient is your R. And so what you guys need to do there, if they do ask you that, is you change this to a decimal, 0.967, and you take the square root of it, right? And that's going to be plus or minus, right? Well, and why is it going to be plus or minus? Okay, when I say plus or minus, I don't mean it as the typical algebra plus or minus. Let me erase it. Your R is either going to be a positive value or a negative value. How do you know which one to choose? If you don't see the graph, it is plausible that could happen to you guys. We know the correlation coefficient. You want to make sure, have that in your notes, know where that is and how to interpret it. Okay, the correlation coefficient is blank. This means there's a linear, positive, strong relationship, or linear, negative, weak relationship between X and Y. Okay, so sometimes on AP tests, you don't get a picture of the data. You just get this output and you have to decide what the correlation coefficient is based on the output. And you don't know if the direction is positive or negative by looking at a graph. But what you can do is you can look at the slope. And if the slope is positive, that means the relationship is positive. So then your R would be positive. If the slope is negative, okay, then your R would have to be negative as well. Okay, interpret R squared. I just put that down as a friendly reminder. That's one of those kind of fill in the blank kind of questions, making sure you know where that is in the notes just for this year, 2020. Normally I'd say I would have you memorize it. And then finally, now it's talking about 65. Would it be reasonable to predict with 65 cars? If you look back up here, The maximum for that X value is 50. 65 is outside of that domain, outside of these X values. 65 is way over here, okay? That's called extrapolation, and that's a risky projection. So no, it would not be reasonable. Okay, let's keep cruising, you guys. We're doing really well. Okay, again, not reading through things, just talking about what is the question asking. Here, the question is talking about describing a method for assigning 24 students to two groups of equal size. Hat method. 24 students, equal size sheets of paper, put them in a hat, shake up the hat. First 12 go to the first group, second 12 go to the second group. At the end, compare the response variable, whatever that is in this question. And I think it's a post-test minus a pre-test score. Okay. All right. This one's talking about volunteers, self-selection. Why is it not okay? Here you want to discuss something about, hey, I have X, right? I have Y that I'm measuring. If I let people choose, now all of a sudden I have a lurking variable. And that lurking variable is, it could be friendship choice. It could, I mean, there's a lot of things you could make up. You just have to read. If I choose to be with my friends, okay, would that increase my score or decrease my score? How could that influence that Y? So now all of a sudden, we don't know if the response, whatever we measured here, is because of the X, or is it because I was with a bunch of my friends and I didn't do so hot, okay? We want to make sure that the Y, whatever happens to this Y variable, the response variable, is because of the X and not because of some lurking variable. And so we can control that by using randomization. All right, again, what is the question asking? We're cruising. Here's some probability. Here, what I did is I just said or, okay? So it's talking about what's the probability that adult is from a college graduate or gets their news from the internet. College graduate is 693 out of 2,500 plus from the internet, 687 out of 2,500, okay? Then you have to ask yourself, can they be both, right? That's that addition rule. It's in your formula sheet. Can they be both? If they can be both, that's right here. You need to subtract that out, okay? So 693 out of 2,500 plus 687 out of 2,500 minus both, okay? They are not mutually exclusive. Mutually exclusive means they can't happen at the same time. These can. Okay, part B, if an adult who is a college graduate is to be selected at random from this sample, what is the probability the selected adult obtains news primarily from the internet? This is a conditional probability without the word given. So probability, what's given? The adult who is a college graduate is to be selected from the sample. CG, what is the probability that they get their news from the internet? So whatever is given goes on the right side of this line. And then what the question's asking is on the left. And when I teach this, I teach it almost like a fraction. And I say, hey, this is my denominator, however many college graduates I have. And when you have a two-way table, just circle the two-way table, whatever the given is, because that makes it easier. That kind of takes away, hey, I'm not going to be using any other numbers. My numbers have to come from this column. The total number of college graduates goes in the bottom. Okay, that's 693. And then in the top, the numerator is always both. That means they have to be a college graduate and get their news from the internet. So that's, I think, is that 245 or 243? I can't read it right now. I don't care. Okay, next, independence. Really, I'm going to talk a little bit slower about this. I think this is really important. I could really foresee this being on the test. It's a common one that's on the test. Okay, so when selecting adult at random from a sample 2,500 student is a college graduate and obtaining the news from the internet independent. Okay, so couple ways to do it. My favorite way to do it is this way. College graduate, right? Okay, has to equal the probability of being a college graduate given, okay, they get their news from the internet. Or you could do it the other way because I have it set up there. It doesn't matter. But where am I going to get that? That's from the formula sheet. Okay. So the probability of A, I lied. Only the probability of A given B is on the formula sheet. So our independence rule, there's another one, but this one's my favorite. This is what, so I'm going to stick with this one. The probability of A given B has to equal the probability of A. Okay. So that has to happen in order to be independence. I do want to just go with you on this one and do this one, okay? So when selecting adult at random, 2,500 students, college graduate, and gets their news from the internet, independent. So I just did it backwards. So I did the college graduate first. It doesn't matter. Okay, so I flipped it. So I didn't do the conditional first. Draw your line, right? Probability that they're a college graduate. I don't care about any conditions. College graduate. How many college graduates do I have? 693 out of 2,500. Again, no conditions here. Now I'm going to look at this one like a separate one, right? Okay. Given they get their news from the internet, that's this row right here. Okay. What's the probability they're a college graduate? Okay. So again, in the denominator, all my internet people, that's 687. In my numerator, both college graduate and internet, that's right there, 245. Divide those decimals out. If they are equal to, they're independent. If they're not equal to, you say not independent. Okay, let's cruise. This one, ELISA one. Okay, so anytime you have like a testing going on, think tree diagram. I'm not going to go through the whole tree diagram. I have done videos on tree diagrams. I can post for it if you need. What I really wanted to just highlight right here is this part B again. Among the blood samples examined in the training program that provided positive ELISA results for HIV, what proportion actually contain HIV? Here they don't always say the probability, they say the proportion, but that's another given. What's given? That they had a positive HIV results. That's given. What's the probability they actually have HIV? Okay. So, another given one. All the ways you can test positive in the denominator. In the numerator, all the ways we test positive and have HIV. Please, 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 I will make a note to put a tree diagram video up so you can watch that if you need. Okay, I'm going to keep cruising, you guys. We're doing really great. I'm not going to do this one. This is just similar to the last one. It's another given one, but they don't state given. So, hey, this person income is over 50,000, right? That's the given. What's the probability they'll be in the 31 to 45 age group? Okay. Again, another independent. This might be a nice one. If you just want to double check if you're doing it right, you can do it. You can pause your screen and do the question. And you can just Google the question because it is a free response problem that's been released. And you can find the answer, or you can send it to me and I can check it and just say, yeah, you got it. Good job. Here, let's talk about random variables. This one's just saying, hey, can you read a chart? At least one of the ATMs is working. So you could say at least one would be 0.21 plus 0.40 plus 0.24 or 1 minus 0.15. Expected value, I've talked a bit about that. Okay, so make sure you know where that is on the formula sheet. But really what you're doing is you're multiplying these all together and then you're adding them up. Okay, make sure you show your work, you guys. Okay, here's another given, but they do say given this time, so that's nice. Given at least one ATM is working, okay, what's the probability that all three are working, okay? So just saying, okay, in the denominator, I need at least one is working. In the numerator, I need at least one is working and 3. Well, that's just 3. So you can figure that one out. So, and then another given one. Okay, so just making sure that conditional probability when they talk about given or they talk about assuming or just seeing that it is worded a little bit differently. I'm trying to kind of go fast because I have a lot to get through. So if there's I'm trying to stay calm and just chill too as well, just because, it's coming up. And like I said, I want you to focus on what you know and just refresh things and not to go crazy. But I think it's valuable just to have some, refreshing things for you guys. Okay. All right. Here we're going to get into some binomial and geometric. Again, not reading the problem, but it just says, what's the probability that Sam's first upgrade will occur after the third flight? Probability of your first success, so first upgrade, geometric, will happen after the third flight. So this is the probability that X is greater than 3. Please, please, please check out binomial and geometric if you need to. Just remember, when it's an inequality, meaning a greater than or less than, greater than or equal to, less than or equal to, it's always a CDF. If it's an exactly something, it's a PDF. The calculator only does less than or equal to for CDF. So you need to rewrite this as 1 minus the probability that X is less than or equal to 3. How did I know that? I knew that because it's 0, 1, 2, 3, 4, dot, dot, dot. The probability that Sam's first upgrade will occur after the third flight. That's anywhere from here. That's what we want. Whenever you have an inequality that's greater than or greater than equal to, you need to do 1 minus what you don't want, okay? Part B is talking that he'll be upgraded exactly 2 times in the next 20 flights. Now we're in a binomial distribution. Exactly means PDF, okay? Next, lastly, another binomial you can use, would you be surprised? So you have to figure out the probability based off now a new fixed number of trials. And then would you be surprised? If it would happen, you're surprised if anything happens when it has a low probability. Why? Because a low probability is an unlikely event, okay? A low probability is an unlikely event. So you're surprised if it happens. All right, let's move on. I want to just talk about, well, I'm just trying to see how much more I want to do. Okay, not much more. I may talk about this in the review tomorrow. I'll kind of decide, but just in case I don't get to it, okay, just in case I don't get to it, let's not worry about it. A and B, I'm going to skip right now. I'm going to go to C. It says, suppose the distribution of fish lengths in the lake is non-normal, but out of the same mean and standard deviation, would it be appropriate to use the normal distribution to compute the probability in part B? Well, in part B, it has a sample size of 50, okay? And we have a mean of 8 and a standard deviation of 7.5. Since the CLT says if n is greater than or equal to 30, we can use that normal distribution. It's okay to proceed, okay? So I think this is a good problem. I'm going to try to get this in our review session tomorrow. But if I don't, I'm going to just have you pause it. You can read through A and B, and then I'm going to go through, and I have the key for A down here, which I think is a good one too. It's just talking about, which one is more likely to happen if you would have something greater than 10 inches. And just to remember that, hey, when we increase variation, right? When we increase our sample size, our variation decreases, right? Okay. So the chances of seeing that extreme observation, you can see by the area under the curve here, is a lot smaller, okay? Is a lot smaller. You can think of it like this. When we flip a coin, right? If we flip it 100 times, to flip 90 tails, that's unusual, okay? The probability of that happening is going to be very small, okay? But if I flipped it only 10 times, okay, and I flipped heads 9 of those times or tails 9 of those times, that's a little bit, that could happen more because when I have a smaller sample size, the probability of extreme observations, okay, right? Because there's more variation. When we have a smaller sample size, there's more variation. So that could happen, right? But if I have a large sample size, the variation goes down. And so the probability of observing extreme observations is not as likely. Okay. All right. Let's move on. Describe the sampling distribution. Describing the sampling distribution, I've talked about this in a previous video. Shape, okay? Well, sample size is bigger than 40, so we know it's going to be normal, okay? Right? Center, mean is 3.9. Spread, standard deviation, 1.1 divided by my sample size. So 1.1 divided by the square root of 40. How do I know I'm using that standard deviation? Well, because we're dealing with quantitative data, okay? And our sample size is bigger than 1, and we have that standard deviation that is on our formula sheet that we use all the time. And this is a Unit 5 type question where we weren't getting into the significance tests yet, but we were just concluding based off probability, okay? So we were taking the information, finding, a z-score or whatever, and describing that sampling distribution versus mean versus proportion. So let's keep going. Here, just does the data provide convincing evidence? You're doing a test. I've talked about that. How do I know what kind of test? Is it 1 sample or is it 2? Okay, this one's 2. Is it a Z or a T? This one's a T because they're talking about the mean. When we have 2 samples, what are we looking for? One sample t-test for the difference of mu1 minus mu2. Okay, here we're talking about confidence interval. It's talking about interpreting it. Make sure that's in your notes. That's a fill in the blank type of question, okay, in context. I do really like part B, okay, and I also like part C because that's stretching your mind just a little bit more, and especially this year in 2020, I think they're going to do that to you a little bit, okay? So it's saying a National Pet Products Association claimed 39% of households owned at least one dog. Well, they gave us an interval right here. So what you need to do is you need to find the lower bound, and you need to find the upper bound. Now, some people, especially sometimes really high achieving students, even really struggle with this because they're so used to typing things on their calculator that they forget what an interval is actually doing. It's a statistic, right? Okay, so that's my p hat plus a margin of error and a statistic minus a margin of error. That gives you your lower bound and your upper bound. So to get your lower bound, you do 0.417 minus 0.119 and 0.417 plus 0.119. Okay, and you get a lower bound and an upper bound. And what you're looking for in this case is 39% contained in the interval. Is it in between that interval? Now, 0.417 minus 0.119 because it's super late right now and I just want to get this one done. I'm going to not do it in my head. 0.417 minus 0.119. Okay, and then 0.417 plus 0.119. Okay, so now what you can see, you guys, is you can see that 39% is contained in that interval. Okay, so does the Humane Society interval estimate provide evidence that the proportion of dog owners in its country is different from this national proportion? No, because our 95, you have to say that, our 95% confidence interval contains 0.39 in it, okay? All right, sorry, I'm so itchy. I was outside all day today, or not all day, sorry. I was working most of the day, but then this afternoon my husband went golfing, so I took the kids to French Park and we were outside most of the afternoon. So, afternoon/evening. How many households were selected in the Humane Society sample? Okay, they don't tell us a sample size, but we do know a margin of error, right? And we know that a margin of error is equal to a Z star times our p hat times 1 minus p hat over our n. Okay, so what do we know? We know that the margin of error is right there. That's 0.119. We know what the Z star, and we know we're using Z. Why? Because we're talking about proportions. Okay, so we know Z star is 1.96, and we actually know our statistic. That's 0.417 right there. Okay, so we take 0.417 times 1 minus 0.417. And we have our n, and now we're going to use algebra and solve for n. Remember, please always round up. You guys, we made it through everything. I'm so incredibly proud of you guys. I will Google Meet with you guys tomorrow for a final review session. And then on Friday, I'd like to meet with you guys just one more time right before the test just to give you my little cheerleader pep talk. So I hope you guys are well. It is late right now. I'm tired, working hard, and you guys deserve this. You're done so soon. So finish strong. I can't wait to hear how it goes. Take care, stay safe, and enjoy the sunshine when you can. Finally, keep smiling.